Okay, and in particular, let's suppose that we have let's suppose that we have bilinear elements right here. It really doesn't matter whether our elements are bilinear or not. It will come in only in a few more minutes, but whatever it is, once we know that we have this partition into element subdomains, we can then go ahead and construct our basis functions, right? So just as we did before, we will construct basis functions. Okay, and here's where things start getting a little interesting. So let's construct basis functions. We know that the way we set it up is to construct basis functions which are defined over every element, right? That's how we do it with this idea of compact support of the underlying basis functions that we are going to use. And I will specify that UH here is dependent upon position and time. Okay, so we want to construct a representation for this sort of function using our basis functions. Right, so we will, as before, expand over the nodes in the element NA. Okay, now here is the here's where we need to really start paying attention. So NA is parameterized by x because after all it is a spatial basis function, but we already know all about that. We know how we're going to construct our basis functions from our by unit domain, right, which is parameterized by xi. All of that is exactly the same. So this is where the spatial dependence of UH is taken care of. The time dependence of UH, right, is done in the sort of formulation that I'm describing here. It is done by simply having the coefficients here, right, which we know to be the nodal values of our trial solution field, right, DAE, right. We just make these guys time dependent. Okay. In this sense, once we've done this, what we are doing is a spatial discretization, right? So this takes care of our spatial discretization. Okay, we haven't done anything to discretize time yet. For this reason, the type of formulation I'm describing, where the time dependence is held in the coefficients, right? This type of a formulation, this type of a finite element formulation is often called a semi-discrete finite element formulation. All right, so this thing is often called a right? Okay, because there is as yet no discretization of time. All right. Interestingly, for WH, let's try to understand what we have. We know that WH is a function of position. Look back at our weak form and think about whether or not we actually need any time dependence in our weighting functions. Is there anything in that weak form? You can look at the finite dimensional or the infinite dimensional weak form, it doesn't matter. Let's look at the finite dimensional because that's the one that we're actually working with. Is there any need for time dependence in our weighting functions there? Right? And indeed there isn't any. Okay? Because it doesn't, there's no time derivative on it. There also is no integration over time, right? So there is really no, and you know, W is something that we specified. We don't really need to worry about any time dependence there. So WH is only a function of position, right? And this we already know, right? We've got this one very nicely covered. right? We have our basis functions which depend upon x through c, and the coefficients here are c, a, e. So this is no different in any manner from what we did with the weighting functions for the steady state problems. Okay? All right. With this in mind, observe that if you are still looking at if you still have in front of you the finite dimensional weak form, right? I'll pull it up again. Here you have it. If you look at it, you will, if you look at the second term on the left-hand side and the two terms on the right-hand side, it should be fairly clear to you that through the entire process of our finite element formulation, right, setting up the element integral as well, first of all calculating gradients of fields as needed, setting up the element integrals, going to matrix vector forms, first over elements, and then doing assembly over the whole domain. None of that is any different, right, for the second term on the left-hand side and the two terms on the right-hand side. Okay? So what this allows us to do is save about 3 segments worth of me talking, and we can simply say from here it should be clear that from here integral over omega wh comma I kappa ij uh comma j dv, right, at the end of the whole process, right, when everything is said and done, it's going to be essentially a C transpose KD, right? We know how this all works out, and nothing is different except for one thing. What is different here? The C is just as before, the K is just as before, the D coefficients are time dependent. Okay? All right? We have that. Integral over omega wh f dv plus integral over the Neumann boundary wh jn ds is C transpose F. Okay, just as before, right? Because here there is no time dependence in C. Nothing is different. Note, however, that right, one could allow a time dependence in the forcing term. Okay, and in fact even in our boundary terms. Okay, so let me make a remark here. Okay, one can have UG equals UG function of time, right? So the Dirichlet function that we use, the function that we use on the Dirichlet boundary, could be a function of time. In fact, so could your influx. Right? There is nothing preventing this. Right? And indeed, the formulation can take full account of it. You could also have F, our forcing term, could be, of course, a function of position, but also of time. Okay? And so, in general, we could have F equals some function of time. All right? Okay. If that's all good, really the only term we need to worry about when you go back and look at your weak form for this problem is the very first term. Okay? It's only this term that we need to worry about now. Let me go to a different color. Right? This is the only term that we need to really focus on here. Okay? And so we will when we return in the next segment.